in math, we work with functions, and really a function is kind of like a rule, right? It takes an input and it gives an output based on like a kind of rule we make, right? Like, so we say every input must be squared. Well, that's just f of x equals x squared, right? A vector valued function is something that takes in a number and it spits out a vector based on a kind of rule. So, for example, a type of vector function could be r of t is going to equal t plus 1, 2 minus 3t, and then we'll say 4t plus, or let's say 4t minus 7. It doesn't really matter necessarily, but this is a vector valued function. So it takes in a number. It could be any number, so I could put in 5, and it would spit out a vector. So r of 5 would equal, so we could say it would be 6, right? 3 times 5 is 15, so 2 minus 15 is negative 13. And then 4 times 5 is 20. 20 minus 7 is, I think, 13. I could be wrong on the basic arithmetic there, but you could see by inputting a number, I get a vector out of this. That's really a vector valued function. So with vector functions, we can do a lot of the same things we can do with regular functions, because of just because of if you like because I guess it really is just made up of scalars, so the scalar math works transfers over pretty well. So for example, if I take the limit, so the way a limit's really kind of defined, I guess, is a limit as t approaches, let's say t approaches 4, right, is really the limit as t approaches 4 for let's see the notation, just make sure, the x component, right? The x component will be some function of t, right? The limit as t approaches 4, and I guess I should clarify, this is f of t, this is g of t, and these are just functions that help determine the components, right? So it's a scalar function, or a vector function is made up of like scalar components that give the component, right? So the limit as t approaches f of g of t, and then the limit as t approaches for h of t. And because this is going to be a continuous function for r of t, right? There's no places where, this is like a continuous function, and we know that because the limit exists for every point, right? If I were to do the limit as t approaches 10, as the limit as t approaches 20, it would all work, for example. But if this was, maybe the g of t was instead like 3 over t, then I know there would be no limit as t approaches 0, and it's therefore not continuous. And to evaluate this limit, it's going to equal, right, when I evaluate this, well, it's the same, because this is a continuous function, it's the same as just plugging in 4. So it's going to be 5, negative 11, I think, or 10, 2 minus 12 is 10, and then 12 minus 7 is 5? That doesn't make sense. Oh, it's not 5. It's 16 minus 7, so it's 9. Okay, point is, the limits, this is how limits kind of work with vector functions. So, if you think about, well, what's a space curve? Well, a space curve, that's another part of this. A space curve is just the path traced out by a vector function over time. So, if you were to think about this, vector function right here, right? So if we say, let's say r of 0, right? It's gonna have components 1, 2, and then negative 7. So 1, 2, and then negative 7, maybe right around like this. So this is r of 0. And now for r of 1, well, r of 1 is going to be 2. Okay, I'm so bad at arithmetic sometimes. 2, -1, and then -3. So let's do this. So 2, and this should really be x, y, z. So it's going to be 2, -1, and then -3. So kind of, I guess, right around there, right? And then if we were to do, let's do r of 2. Excuse me. So r of 2 is going to be 3, 3, negative, oh my god, I hate doing the math in my head, -7, a -7, and then 5. No, I'm doing 2. So 3, 2, -4, and then 1. So, or 3, I guess. 3, and then negative, let's see, negative, what was it, 4? I guess something like this, and then 5. And it's a little hard to see right now, but what you would essentially get when you connect the points, all the tips of these vectors, I kind of completely butchered that. You get a line though. So the space curve for this function is a line, because the path that it traces out will end up being a line, right? And this actually like kind of makes sense, because really this is just this r of t. If you were to think about the point, so consider a point on this point P, right? Any point on this line will have an x value that's equal to t plus 1, y, which would be 2 minus 3t, and then z is going to equal 4t minus 7. So these are really the parametric equations for a line for any point with coordinates x, y, z. So the vector function, right, it starts from the origin and then it points to like a point x, y, z on the line. So it makes sense why a space curve would be equal to, or why the space curve for this vector function in particular would be a line. Now if you have, let's say you have a vector function, right, that looks something more like, cosine t, sine t, and then t, right? So if we think about what might the space curve for this look, well, we know that the t will the z component, right? So let's just kind of get this just so we know which help us with determining which component's which. We know the z component is going to be t, so over a time t, right? Like as t increases, then I know that my z component will also increase linearly, right? Or I guess linearly might not be the right word, but hopefully you kind of see if I double the input, my z component doubles as well. I guess that's kind of what I mean by linear. So the z component will increase indefinitely, but cosine t and sine t, well, they cosine t, right, for the x component is going to oscillate. It's going to go back and forth, back and forth. For sine t, it's the same thing, right? Sine t oscillates from -1 to 1. So if my z component's increasing, but my x is going to oscillate, right, and my my y is going to oscillate as well, then I get this helical pattern, right? I get this helical pattern around the z-axis, and this should kind of actually make sense, because we know for usual parametrics, right? If you think about the y-x parametrics that you might have done in pre-calc, or I guess in Calc BC as well, we know that, hey, if y of t was equal to sine t and x of t is equal to cosine t, then I know this would create a circle. And I know this would create a circle because when I eliminate the parameter, I get x squared plus y squared is equal to 1, right? Where you have cosine squared t plus sine squared t would equal 1. So when I eliminate the parameter, I get the equation of a circle. And essentially what you're getting is a circle that's extended on the z-axis because the z component is increasing indefinitely. So in a really similar way, we can actually get, and remember, this is not really the function itself, right? The function really creates vectors from the origin that point to points on this space curve, right? The path traced out by the tip of the vectors increasing over time, that's the actual space curve. So we can actually, in a similar way where we can eliminate the parameter and figure out what kind of a shape a function might give us, we can actually do the same thing for vector functions. So an example would be, let's say, let me get an example just from my little thingamabob. So let's say we want to figure out what is the let's say we'll want to find a vector function. So example, find a vector function for a curve that represents the intersection of two surfaces, right? The intersection of two surfaces. So we're going to have the two surfaces in question for this example are going to be the cylinder x squared plus y squared equals 4, and then z equals xy. And really quickly, I'm just going to go to Desmos. I'm just going to show you what this actually looks like. So Desmos 3D. And then let's just get an x squared plus y squared equals 1, and then we can extend to 3D. And then we have z equals xy. So what you see right here is for these two shapes, right? They intersect and they create this sort of curve that kind of goes up and down, up and down. Hopefully you can kind of see that, right? It kind of goes up and down, traces a circle over here, but it's kind of going, if I draw this down and then up and then down and then up. So what would be an actual vector function that could create that kind of curve? Well, to figure this out, what we kind of have to say is, well, look, for our x and y components, we know that they have to conform to this, right? Meaning, like, for our vector function, like, if we think about our if we think about our vector function, r of t equals f of t, g of t, and then h of t, then I know that, hey, when I take whatever f of t is and whatever g of t is, when I square them both and then add them together, I know it needs to equal 4, right? So, and I think that was the question 4. I know, like, that needs to be true. There's that kind of restriction, right? And what would be something that if you took a function squared and you add it again squared, or add another function, add the square of another function, it would equal some constant. Well, that's just Pythagorean theorem, right? So I know, hey, cosine squared t plus sine squared t is going to equal 1. If I multiply both by 4, I get 4 cosine squared t plus 4 sine squared t needs to equal 4. So this would be 2 cosine t squared plus 2 sine t squared. 2 cosine t will end up being my f of t, and then the 2 sine t will end up being my g of t. So that makes sense, right? If we're trying to look at the intersection of the points, I know that, well, it's the curve of intersection will always be on that cylinder, which will always be circular. So you need to have two functions that are both sinusoidal that creates like that circular shape, right? If f of t was t and g of t was like t squared, something random, well, what that would mean is that the vector would then leave, right? It would leave the cylinder, right? If it was t and then g of t, if t, like, so let's say if f of t equals t, and then if g of t equals t squared, then the vector itself would point out here at like t equals 20, right? It would leave the cylinder. So it needs to be cosine t and sine t so that it's the domain and the range, or I guess the range is restricted within the actual cylinder, right? Hopefully that makes sense, right? That's the reason why it makes sense that it should be cosine t sine t. Now to figure out h of t, it's very simple from there. You just got to say, hey, I know z is going to equal sine t times cosine t. Now, this is actually equal to 1/2 sine 2t, right? Because, or I guess in this case, it would be 4, so you would have 2 sine t times 2, so you would have 4, right? Because you're doing 2 sine t times 2 cosine. I should just draw that. That's probably a little confusing. It's going to equal 2 sine t times 2 cosine t. It's going to equal 4 sine t cosine t, which is just going to equal, we know 2 sine t cosine t is equal to sine 2t. So this is 2 sine 2t. So our final vector function will end up being, so r of t is going to equal, and you can even pull the 2 out if you want, sine t, cosine t, and then sine 2t. I can pull the 2 out because when I distribute the 2 over, I just get the 2 cosine t, 2 sine t, 2 sine 2t. So yeah, this is vector functions. And hopefully, if we look back to the curve, right, this actually makes sense because this result makes sense because, oh, I deleted it. Okay, you could see that, like the z component, right, the height of this curve on the z-axis, right, it's also oscillating back and forth. Excuse me, sorry. The z-axis is oscillating. Oh my God, this is going crazy. The z value is oscillating, the x and y value is oscillating, so it's going to be, the components are going to be oscillatory in nature. Like the periodic in nature, right? They go back and forth. So yeah, this has been a little intro to vector functions. Hopefully this kind of makes sense, the whole idea. I don't think this is actually too like crazy of a concept. So yeah, thank you for watching. Hopefully this video made sense to you.